Okay, in this video let us discuss the sequential circuit design procedure which uses T flip-flops. Okay, so in the last lecture we have discussed the design of a sequential circuit using JK flip-flop. Okay, now let us demonstrate the design procedure by using a simple example. So I would like to consider a binary counter. Okay, let us take a binary counter and design the binary counter using T flip-flop. Now let me take an n-bit binary counter. So if I take n-bit binary counter, then this counter will consist of n flip-flops, capital N number of flip-flops. Therefore, whenever you have capital N number of flip-flops, then you can count from 0 to 2 to the n minus 1. For example, if you take n is 3, then you start from 0 0 and then 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So there are 8 counts, totally 8 counts. This is state 0 0 and this is 7. 7 is nothing but 2 to the power 3 minus 1. Now let us draw the state diagram of a 3-bit binary counter. So you start from 0 0 and then increment by 1, you go to 0 0 1. In fact, if you before that you start 0, go to 1, 2, 3, 4, 5, 6, 7. You connect these lines. So this is the state diagram of a 3-bit binary counter. Okay, once you reach 7, then you come back to 0. So now instead of writing in this method, I am going to assign the number, binary numbers. Assign binary number. Recall the design procedure. Okay, so we said there are 7 steps while designing the sequential circuit. So 0 is denoted by 0 0 0 and 1 is denoted by 0 0 1 and then 2 is 0 1 0 and 3 is 0 1 1 and 4 is 1 0 0 and 5 is 1 0 1 and 6 is 1 1 0 and 7 is 1 1 1. This is the state diagram of a binary counter, 3-bit binary counter. Bit binary counter. Okay, so look at the diagram. The binary states are indicated inside the circle 0 0 0 0 0 1 and so on and so forth. Now the flip-flop outputs repeat the binary count sequence with a return to 0 0, return to 0 0 after 1 1 1 1 1. Okay, notice that the directed lines between the circles, okay, this circle to this circle, this directed lines are not marked with the input and output values. Okay, we are not discussing input and output values here. Output values. As in other state diagram, if you look at other state diagram, we had input and output. Here, especially in counters, only the states are enough for me. Okay, the states are the outputs. Okay, so because I am counting, okay, counting events, how many generally when you take a counter, as I said, the counters can be used to count number of people, to count number of events, to count number of things, to count seconds, to count minutes, to count hour, like in your stopwatch, in your alarm, right? There are many places we can use it. Therefore, the state itself, I'm going to use it. Okay, the moment I start, for example, if you take your digital watch, then you start from 0 0. This it's a starting point, 0 1 first second, second second, third second, like that. You have 60 seconds. So this is 0 0 is a present state, and 0 1 is a next state, 0 2 is a second, third state, and keep on goes. And that is going to be my output also. Okay, that's what I want. The whole purpose of designing the counter is whatever there in the state, that I am going to use it. So there is no explicitly input and output for designing a counter. So that point you should remember, and you should distinguish from the other designing things. See, other sequential circuits are designed for some other purpose. Okay, so you will give some input and get some output, and the sequential circuit will do some operation and gets the desired output. But here the counters are slightly different from the conventional sequential circuit, in the sense that the state itself I am going to use in the counter. Okay, therefore we don't have input and output values as in the other sequential circuits. Okay, so that please remember. So remember that state transitions in a clocked sequential circuit are initiated by clock edge. Okay, so the flip-flop remains in their present state if no clock is applied. Okay, see, suppose there is a big room, big hall or auditorium, and you put some sensor here, and sensor will give one clock pulse like this if one person enters inside the hall. Okay, so you put some transmitter here, and you put some receiver here. So the moment one person enters, that signal will be disturbed between transmitter to the receiver. So this sensor will generate this clock. As soon as the clock goes to the counter value will be incremented. So here the input to the counter is not from the in this example, not from the oscillator or somebody else, somewhere else. Okay, here the input is coming as soon as one person enters inside the hall. The moment a person enters inside the hall, then this pulse will be generated and the counter value will be incremented by 1. If no person enters, then there will not be any change. The counter will remain in its state indefinitely. Okay, for example, one person enters at let's say now time is 6:45 a.m. and then after 5 minutes up to let's say up to 6:50 a.m. no person enters. So that means next 5 minutes the counter waits in the same state. Let's say at 6:44 a.m. there are 51 persons in the hall. Then 6:45 one person enters, then the counter becomes 52. And then 6:45 to 6:50 until this time the counter stays in the 52 only. It will not go to 53 until you give the clock, until the person enters inside the auditorium or hall. Okay, so the counters are nothing but it is a clocked sequential circuit, and the states are changed. The counter goes from the present state to the next state only when the input clock is applied. If no clock is applied, the flip-flops remains in their present state. That's it. Okay, so for that reason, no, the clock does not appear explicitly as an input variables in the state diagram or a state table. So we will not put a clock in the show the clock in the state table or in the state diagram. Therefore, while designing counters, two things you need to remember. There is no explicit input and output. Okay, first point. And second point, in the state diagram there is no column to denote input and output. The state itself we are going to use it, that's the purpose of your counter, right? So that is why I said we don't say any input or output. The input to the input to the counter is only the clock, okay, and the state itself we are going to use it. If suppose if I design, if the present state indicates like 74, see the event starts at 8 o'clock. You wait until 8 o'clock. The moment you reach 8 o'clock, you close the door and then look at the counter value. Let's say the counter value is 74. So this is the present state of the counter. Present state of the counter at 8 a.m. in the morning. Okay, at 8 in the morning. That means what? 74 persons have entered inside the auditorium. Okay, so that is my output. So the present state at 8 o'clock is my output. The counter value, the state at what it has. And what is the input? Clock. So as soon as a person enters, the clock is going to increment by 1. So I don't want to explicitly put this clock thing in the state diagram. So for this point of view, the state diagram of a counter does not have to show input and output values along the directed lines. If you recall, from the previous lecture we wrote 0/1 or 1/0 or 0/0 like that. But here we are not going to do anything. Okay, as I said, the only input to the circuit is the clock, and the outputs are specified by the present state. I'm sorry, output, oh my god, present state of the flip-flops. So output is nothing but the present state of the flip-flops, and the inputs are nothing but, the input is nothing but the clock. So if you look at the diagram, let's say I am at this state 0, 1, 1, okay, 3. The next state is 4, right? So the next state of a counter depends entirely on its present state, and the state transition occurs every time the clock goes through a transition. As soon as you apply the clock, there will be a state transition from the present state to the next state. Now let us form the state table for this 3-bit counter. State table for 3-bit counter. Now there are 3 bits, right? Therefore I need 3 flip-flops. So let me denote those flip-flops as A2, A1 and A0. Now you start the present state, let me write it properly. A2, A1, A0, right? So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and all are ones. So this is 0, 1, 2, 3, 4, 5, 6, 7. Fine. So this is present state, and let me write down the next state. So the next states are going to be let's say this is A2, A1, A0. When you are in state 0, 0, the next state is 0, 0, 1. Then fill it up as usual. When you are in state 1, the next state is going to be 2, 0, 1, 0, 3, 0, 1, 1, 4, 1, 0, 0. One state ahead. okay, and then here 1 0 1 1 1 1 0, then all triple 1, and after 7 you should go to move back to 0. That's it. This is my next state. Now let us write down the inputs, flip-flop inputs. Okay, so how will you write down the flip-flop inputs? It's very easy. Okay, it's not like as complicated as JK flip-flop. I will not say JK flip-flop inputs are complicated, but people sometimes they will think that it is complicated because 0x x0 1x x1. If you don't understand, then it is complicated. Otherwise, within a fraction of a minute you can fill it up and you can finish it. Fine. Now flip-flop inputs. Flip-flop inputs. Now 0 to 0, no change. T suffix A2, T suffix A1, T suffix A0. Flip-flop inputs. This T denotes T flip-flop. That's it. Now 0 to 0, no change. Therefore, the input is 0. Recall the input excitation table of T flip-flops. Let me write down here. 0 to 0, input is 0. 0 to 1, there is a change, toggle. 0 to 1 is toggle, right? So input must be 1. 1 to 0, there is a toggle 1. 1 to 1, no change, so input is 0. This is the characteristic table of, excitation table of your flip-flops. See, present state is 0 and next state is Q of t plus 1. This is TA, input to the flip-flop. Now 0 to 0, no change. When there is no change from present state to next state, the input must be 0. As long as the input is 0, there is no change in the T flip-flop. If 0 to 1 toggle happens, therefore whenever you apply 1 to the T flip-flop, the present state will be complemented. And 1 to 0, present state is 1 and next state is 0. You are complementing the present state. So the input must be 1. And 1 to 1, no change. Therefore, this is 0. So this is the excitation table of, it's very easy. Table of T flip-flop. Okay, so same thing we are going to apply here. Now 0 to 0, no change, 0. This one 0 to 0, no change, 0. But here 0 to 1, I should put 1 here. And in this 0 to 0, no change. 0 to 1, yes, I put 1. And 1 to 0, yes, I put 1. Change toggles. And here 0 to 0, no change, so the input must be 1. And 1 to 1, no change, so the input to the flip-flop must be 1. And 0 to 1 toggles, so I put 1 here. And then 0 to 1 toggles 1. 1 to 0 toggles 1. And 1 to 0, 1. All are 1s. Okay. And then let me change the color. Let me put a red. 1 to 1, 0, no change. 0 to 0, no change, 0. And 0 to 1 complemented, so 1. 1 to 1, no change, 0. 0 to 1 complemented, input is 1. And 1 to 0 complemented, 1. And 1 to 1, 0, no change. Again 1 to 1, no change. 0 to 1 complemented, so I put 1. And here 1 1 1 2 0 0, all are complemented, all bits are complemented, so everything will be 1. That's it. So that's how you derive the flip-flop inputs. Now I have 3 columns. One column for TA0 and another column for TA suffix 1 and third column for TA suffix 2. So there are 3 columns. So draw 3 K maps. Okay, function of the present state A, B, C. Sorry, I changed the notation. I'm sorry. Let's say A2, A1, A0. Okay, here I am denoting the flip-flops by A2, A1 and A0. And one important point I forgot to tell you here, that binary counters are constructed most efficiently with the T flip-flops because of their complementary property. So generally people will prefer a T flip-flop whenever they want to count, whenever they want to construct binary counters. Now this is min term 0, M0, M1, M2, M3, M4, M5, M6, M7. So this is M0, M1. Let me draw clearly. Let me take some more space and then draw it properly. I think all of you familiar with the K maps. M0, M1, M2, M3, M4, M5, M6, M7. This is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, A2, A1, A0. So now you can fill it up. M0 is 0. Look at here. M1 is 0. I'm taking this column. M2 is 0. M3 is 0. Sorry, M2 is 0. Okay, M3 is 1. M3 is 1. M4 is 0. M5 is 0. M6 is 0. M7 is 1. Good. So now you can simplify this and then you get a expression. So one second, let me okay. Therefore this is A2, right? T A suffix 2. So you can combine these two guys. Therefore this is A1 and A0. Similarly, you can find out TA1 by looking at the middle column. And let me write down directly the answer. You can work out to get the answer. And then TA0. Look at TA0 beautifully. Okay, so this TA0, if you draw the K map, all entries are 1. See, 1, 1, 1, 1, 1, 1, 1, 1, all are 1. So therefore the K map contains 1, 1, 1, 1, 1, 1, 1. If all are 1, then the expression TA0 is 1. That's it. Okay, so that's it. Now let us draw the diagram for this. I have 3 expressions, so take 3 flip-flops, 3 T flip-flops. My diagram is not good, please bear with me. This is CLK. CLK means clock. CLK, and give the common clock to everybody. Clock, and this is A2 flip-flop, A1 flip-flop and A0 flip-flop. This is A2, A1 and A0. Now how these inputs are connected? This is TA2, TA1 and TA0. TA0 is 1, right? So therefore connect this TA0 is connected to permanently logic 1. And what about TA0 is 1. What about TA1? TA1 is A0. So take this A0 and bring it and connect to TA1. What about TA2? TA2 is A1 and A0. Therefore you put a AND gate, and then you take the input from here, and another one is A0. This is TA2. Therefore I have 3 input equations. With that 3 input equation I can construct the binary counter using T flip-flop. Okay, so using these functions with these 3 flip-flops we obtain the logic diagram of the 3-bit binary counter. Okay, for simplicity rest of the signals I didn't show here. Okay, actually when you design a counter, the counter must include a signal called preset and clear. So that I did not show here, but it should have, okay, it must have this preset and clear. So that's how one can design the counter using T flip-flops. It doesn't mean that you should use only T flip-flops. Okay, you can use a D flip-flop and you can use a JK flip-flop as you like. So let me stop here. Thank you very much.